All right. So yeah, my name is Alex, and I'm a recent prof in Montreal, at the University of Montreal, and at Mila, which is the Quebec AI Institute. And I want to talk today about a new data set that we've recently released for solid-state batteries. But I want to start with the motivation of why we worked on this data set, what we want to do with that, which speaks about kind of the general approach we have in our group to tackle this problem of material discovery with machine learning. Which, by the way, my background is machine learning, not material. So I apologize in advance if I say wrong things. That's why I'm here, to learn from all of you. Hopefully, I can also show some interesting things too. Will this switch? Second. It looks better now. Okay, there we go. So like I was saying, my work is on applied machine learning. In general, it's about, I try to motivate my research by the things I care about. One of the things I care about is the challenge of climate change, right? And yeah, we saw a little bit about this in Kulbert's presentation. I think it's important to remind ourselves, even if we see this very often, that we live in a thank you, in a warming planet. It's a very important problem. I think yeah, each of us can do things according to our reach and capacities and skills. So at some point, with my machine learning background, I was thinking of whether I could use the knowledge or the background I had in machine learning for the problem of climate change. And this was like about 5 years ago or so. And one of the things I read was that, yeah, actually discovering new materials was a promising avenue. And that's why I got into that. Actually, I read it, for example, in the IPCC report. They highlight very much how we need to improve energy efficiency, how we need to discover better materials, etc. So again, this is no news for most of you. I just want to make it explicit. All right. So in general, I try to develop machine learning research. I try to do machine learning research that can be useful for these problems, for science in general. In this case, I'm going to talk about material discovery. I also work in part on the drug discovery side, for example, antibiotics. And something I find very, very interesting and exciting is that it goes kind of both ways. It's not just using machine learning for material discovery as, okay, we have a bunch of methods, let's use them. But actually, as a machine learning researcher, working in this area is very fruitful in terms of developing the frontiers of machine learning research, because it forces us to work on things that are new, that are going to have a potential impact, etc. So I think it goes both ways, and I find it's very, very interesting. All right, so to motivate how we use machine learning specifically, I think it's worth saying a word about, we've seen this many times, but saying this word about how traditional discovery works, right? So usually there's some sort of what we call oracle in our machine learning terminology. So this is a source of information that is generally the best thing we can do. It can be running an experiment in the lab. It can be some simulations. Depends. Depends on the problem. It's gonna take a different shape. And usually, doing these experiments, whatever it is, gives us some data, and this data informs, the scientists and gives us some experience that we can turn into new questions, new queries, new hypotheses, etc. Someone has mentioned before how this goes by intuition, or used to go by intuition. It could be intuition, but I think there's a lot of knowledge coming from the experiments, right? So I'm a machine learning scientist. Like I said, I see data and in this model or scheme or loop, and then immediately the obvious thing to do with some data is to train machine learning models with it, and that can improve things by a lot. And in certain applications, this is enough, because what we can do is, well, instead of using this, instead of querying this very expensive or computationally expensive, time-consuming Oracle, we can use our machine learning model and make predictions from it. This, depending on the application, is going to be very successful if the data we have is rich and abundant, or it can be quite inaccurate and not catastrophic, but it won't be very useful. In certain problems, the ones we're talking about, there are so many candidates we could experiment, we could try, that this approach is actually, yeah, it's not even that it's not efficient. It's almost useless. And I would like to make this point. So even if the machine learning model is super accurate, like, you know, as accurate as you want, even perfect, and even if it's super fast, as fast as you want, just with that, we won't be able to do much, because there's no time in our lifetime to evaluate the overwhelming amount of conceivable candidates, right? And of course, I'm giving very ideal conditions. So yeah, again, some people have characterized or estimated the amount of conceivable stable materials to 10 to the 180. I think I've seen it in some slides before. I don't know if this is true or not, but again, it's to make the point, it's not even necessary to have a precise quantification of that. So we need something else, and this something else can be generative models. A generative model in the loop has the potential of making a much more efficient search of this space, and especially if we complement it with, you know, with the intuitions of scientists. And again, this can be trained with data. This can be trained with the machine learning model. There's different things we can do, and altogether, this is I want to make the point that this is a quite promising approach. And I want to highlight here that there's three types of machine learning in this scheme. There is the machine learning model here, and this is what we would call predictive models. So they are able to you know, given an input, they predict maybe a property or several properties of it. There is the machine learning, sorry, the generative model here on the right. We also use sometimes or I hear the word to predict new materials, predict new crystals. I find that sometimes confusing, so I would say generate. This is a model that generates new objects. In this case, it could be crystal structures. And then there's a third machine learning model here, which is the whole thing. And this whole thing, this whole loop, is what we call active learning. And there's going to be some elements of machine learning that are kind of abstracted away from this image, but there's some learning going on in, for example, deciding which queries we want to submit to the machine learning model or to the Oracle and so on. I won't talk about that today. That's part of another branch of research we do in our group. Actually, very interesting and very promising as well. Yeah, I wanted to highlight that there are these three modalities of machine learning. All right. So I talked about this last year, but I thought it was relevant to go very quickly through it, because I think it could motivate the data set that we have introduced that I was talking about before. So I'll try to go quite quickly. Can you give me like time? Thank you. Right. So this is a generative model. We call it Crystal GFN. It's a type of GFlowNet specific for crystals, and this GFlowNet is a relatively new generative model that has several interesting properties. Unfortunately, I don't have time to give you the details of that, but I'm very happy to talk about this later, and coffee breaks, dinners, whatever. But essentially, something that's already different from other generative models for crystal structures is that it introduces a lot of domain knowledge in the model. instead of training it with a data set and see what happens, which is what a lot of models or methods do, what we tried here is to bake in a lot of constraints and properties from crystallography, for example, from theoretical crystallography. So, for example, constraints regarding the space group, the lattice systems, the crystal systems, the crystal families, the point groups, etc. So let's try to generate crystals according to these symmetric properties, and so on and so forth. We don't, unfortunately, like I said, I want to keep this relatively short. But what this generative model does is, instead of optimizing atomic positions, like the raw atomic positions, or even just the composition, it tries to generate sequentially the properties, the descriptors of a crystal structure. It's quite flexible, but one possible way of doing this sequentially is by generating first the space group that we want. For example, it could be 225, and this is decomposed into subparts of the space group. So, for example, we could select the crystal system first, the point symmetry, and then the space group, or a different order. Again, it's quite flexible. Then it generates the composition. So, for example, it selects one element, and then how many atoms of that element, then another element, how many atoms of this new element, and so on. So, for example, we could have 8 lithiums and 4 oxygens. And finally, it generates the parameters of the lattice, so the lattice parameters, A, B, C, alpha, beta, gamma. And you see some lines, some dashed lines going on between the different blocks, and they represent constraints. So all these blocks they constrain each other. So if the space group I selected here is cubic, like the example on the slide, then the lattice parameters are going to satisfy the constraints imposed by a cubic space group, which is like A equals B equals C, and alpha beta gamma equal 90. Like, this is a hard constraint. It's not that approximately it's going to learn from the data to do that. It's going to be a hard constraint. And there's a bunch of those kind of baked in the model. So at the end, we have a description of a crystal with these properties. And then I want to stop a moment about this. The way it is trained is with a proxy model of a property. So I'm going to show some examples later. But imagine that we want to generate crystals with high ionic conductivity, as we will do later. Then if we happen to have a proxy model of the ionic conductivity of a crystal structure, so something that gives me a prediction of the ionic conductivity, then we can make this the reward function of this generative model. And what GFNets learn to do, what they are designed to do, is to sample objects, in this case crystals, proportionally to this reward function. And this has two immediate consequences or properties that are interesting. One is that if we sample proportionally to the reward function, we're gonna sample objects with good scores of our property. So in this case, it would be crystals with high ionic conductivity. And because we're sampling proportionally to the reward function and not optimizing it, we're also going to get diversity. It won't focus just on the best according to the proxy model, but it would get, in principle, give us multiple objects in the optimization, or not optimization, in the search space with high values of the proxy function, the reward. Does that make sense? Okay, good. So this has a number of advantages. I think I've been mentioning them, so I'll move on and come to this later in the questions. But maybe I want to highlight this last one before, in relation to what we were discussing before in one of the previous talks. I think it was Adrian. So Adrian mentioned that, what we do with generative models is to train the model to match the distribution of a data set. And actually, this family of of generative models, GFLNets, they don't do this. And depending on what you want to do, this might be a good thing or a bad thing. But for the problem of scientific discovery, for material discovery, this is actually, in my opinion, a nice property because it doesn't stick to a training data set. Actually, you can train this model without a data set. What you need is this proxy model of a property. And what it does, again, is sample proportionally to it. So no data set, it samples, it learns from a proxy model of a property. All right, and yeah, and the rest of the advantages that I list here is that there's flexibility in a lot of different dimensions. And hopefully, I'll make the point in the next few slides. I have some results using the formation energy and the electronic band gap and the density. I took it out of the slide, so I'm going to show you those. What we have to do, again, I'm insisting on this, is to have a model of this property. So in the case of the formation energy, it is a model that we train on a data set to predict the formation energy, and the error is pretty low, so it's pretty low enough to do this kind of thing. And same thing for the electronic band gap. For the electronic band gap, as you probably know, it's a much harder task. So the model is not so accurate, but well, we can still do it. So about the formation energy, hopefully this slide is to convince you of how this works. If we take the materials project data set and we plot the distribution of the formation energies, this is what we get. Quite biased towards low formation energies because most of the materials in materials project are stable. So this is the distribution of the data set. It says validation set here, but for what it's worth, so it's the distribution of formation energies in materials project. Then, if we initialize this crystal GFLNet that I'm talking about, and before training it, you just sample 10,000 structures, 10,000 crystals. That's the distribution we get, pretty much biased to positive energies because, yeah, it's random structure, not optimized. So most of them are high, not good. And then the main result is that after training, we get this distribution here on blue, which is telling us that from these 10,000 crystal structures that we sample here to do this plot, the distribution of formation energies is even lower than for the validation set. That's good news. Yeah, I'm going to show you a similar result for the band gap. In the case of the band gap, the experiment we did to check whether it works or not is to select a specific band gap, so 1.34 in this case, and train the model to sample crystal structures with a predicted band gap that is close to this value. And again, this is the distribution of the validation set. Obviously, not at all biased to this number, which is relatively, it's not arbitrary. It's important for photonics applications. But yeah, validation set distribution. This is the distribution from a random crystal GFLNet, so pretty bad, obviously. And that's the distribution we get when after we train the crystal GFLNet. So it starts getting closer to the desired value. And by the way, it's pretty easy to force it to be even more selective for that number. You just have to play a little bit with the parameters. In this case, we were a little bit selective, but not a lot. But that's something you can play with, making more selective if you really want to sample only in the close neighborhood of the desired value. All right, so hopefully this makes the point. This slide is to show that there is a lot of diversity in the samples. I'm going to ask you to believe me about this. I just want to move on. But the generated structures have a lot of diversity in general. This is a general feature of the method of GFLNet, diversity. So it's not a surprise. And I would like to highlight also this possibility of what we call restricted sampling. So after you have trained your crystal GFLNet, because of the flexibility in the generation process, it's not doing some fancy but also kind of weird diffusion that generates from noise and then comes up with a structure. Here, it's very clearly defined steps like, okay, space group, composition, lattice parameters. So you can actually take your pre-trained model and say, okay, now I only want compositions with iron and oxygen and with a maximum of 10 atoms per element. Or I want this kind of ternary space. Or I want only cubic lattices. Or I want lattice parameters between 75 and 135 degrees and between 10 and 20 angstroms in the lattice length. Things like this. These are more or less arbitrary decisions that we, arbitrary conditions that we set in order to kind of evaluate this possibility. But you have a lot of flexibility. That's the point. So let's call these four conditions A, B, and C, and D, A, B, C, and D, and see what happens. So essentially, again, this is formation energy. And what we see is that even when we restrict the model to sample with these kind of more restricted properties, it still does the job of sampling structures that are diverse and have low formation energy. Okay, so with that, I will move to the presentation of this new dataset that we have recently introduced, which is about crystals with ionic conductivity measurements. Before that, is there any question about the crystal difference? Something that's not clear at all? No. Okay. So we want to do exactly the same that I have shown with the formation energy and the bandgap. We want to do it for ionic conductivity, right? So ideally, we would like to train a crystal GFLOW-net that tells us that generates structures, crystal structures, with high ionic conductivity. Now, the main problem here is that we actually need this proxy model to predict the ionic conductivity. For those of you, probably most of you who know how you can measure the ionic or estimate the ionic conductivity, well, you can do it experimentally, and it takes months or years sometimes. You can do it with DFT, and it actually takes very long because you have to do diffusion at different temperatures and then do extrapolation. It's time consuming. And that's the reason why there is very, very little data. And there's especially very little data of experimental measurements. This is a table. So there's little data, which means we cannot easily train good machine learning models for this problem, right? So then without that, we cannot use our crystal different, but you can also do any other generative model. You like the data. This table is a summary of the data sets that we have found in the literature with experimental measurements of the ionic conductivity. So there's a bunch of them, but we found a bunch of problems, okay? Sometimes the label, so the ionic conductivity in this column, either does not specify the temperature of the measurements, or yeah, it's a temperature which is not room temperature, so there's not much you can do about that because you want the ionic conductivity at room temperature. And then other problems are related to the information that is contained in the dataset. So it's very heterogeneous. Sometimes you have the composition, but you don't have the space group, right? Sometimes you don't have any information about the lattice parameters. In many cases, you also don't have the zip file to have the full structure. So we decided to try to make sense of this heterogeneous literature and compile a data set so we haven't done ourselves the measurements. It's a compilation of what's in the literature, clean it up, filter things, take zip files from different sources. So it was a lot of manual labor of course, domain experts, not like me, so collaborators. And the result is this data set we have called Obelix. open solid battery electrolytes with lithium, an experimental data set. In total, it has 599 structures, materials. 321 of them have the C files. The rest have the rest of the information complete, and all the measurements of ionic conductivity are at room temperature. And we filtered out a lot of the entries that were more dubious or duplicates and so on. And I'm gonna show you these details. So first, what we did is build a dataset from the Liverpool Ionics dataset, and Laskowski and colleagues from a couple of years ago. And from there, we selected the materials for which the experimental room temperature, ionic conductivity, the space group, and the lattice parameters were available. We discarded everything else, because then it wouldn't be helpful to train machine learning models. At least for now, we could include, or we are actually planning to include new data now, but for start, that was our first requirement. And we got the composition in the cases where it was not explicitly there from the Z number. And then we filtered the data set for exact duplicates. And then we ensured that the near duplicates were correctly captured. This actually, we realized that there were a lot of duplicates in the different data sets. So there was a lot of redundancy in the availability of data, which is understandable, but it was important to get these things right. So in the end, again, 599 unique materials. And we tried to get C files for as many as possible, but not all of them had it, of course. For that, we had to get into the ICSD datasets, in materials projects. Again, some duplicates there. In some cases, many cases we found exact matches, but in many cases we figured out a way to get approximate matches, and we got a little bit more data. And we talked to the ICSD people, and they let us keep the data in, the entries from ICSD in our data set, provided we added a little bit of Gaussian noise to the data, so that's good. And yeah, in the end, there's 321 materials with SIFs. Okay. This kind of Venn diagram shows a little bit the overlap in the data. So you see a lot of overlap between Laskowski dataset and ICSD and so on. And then from a machine learning perspective, it was very important to ensure a rigorous data split, because otherwise, if you don't do like a rigorous data split between train and test, there's a big risk of fooling ourselves, and then that's going to have a big impact on the progress we make in the field. So we did a lot of work on this and try to be as rigorous as possible. So for example, something that we found that is not done in general in a lot of data sets is that we ensured that the training set and the test set had to contain, I would say it in a different way, materials that were presented in a paper, in the same paper, need to be in the same set. So all in the train set, all in the test set. Otherwise, there's what we call data leakage. That leads to, again, what I was saying, fooling ourselves when we get the machine learning results. You think that your model works very well, but what's doing is learning to predict what's in this data, in this paper or in that paper, and that's not what we want. We also wanted to have approximately the same distribution of the ionic conductivities, the same amount in train and test of entries with CF files, and we wanted a test set between 20 and 30% of the data. So those are more or less the conditions. There's a few other things, but these are the main things. And in the end, what we get is this distribution of the elements from the periodic table. Nothing too surprising here. This is, again, what's available in the data set. But something interesting, as we said, we get slightly different distributions of the space groups between test and train. And this is actually a good thing because it makes it challenging, which is a good way to really measure whether your machine learning models are generalizing to different properties or not. But a good coverage also, which is important. There's a diversity of space groups in both cases. This is the distribution of the ionic conductivity, which, like I said, we more or less forced it to be similar in between train and test set. There's a bias towards higher ionic conductivities, obviously, because those were the proposed materials in the papers. And then last thing, so we also wanted to evaluate a bunch of different machine learning models to see, well, how they perform with this data set and with this split. And I'm just finishing with this. Something interesting is that we took about these 5 more or less fancy recent models from the literature and trained them with our data or fine-tune them with our data and so on. And what we found is that they all perform pretty poorly. Actually, this baseline median prediction is the mean absolute error. If you just take the median from the training set and use it on the test set, that's what you get. And you see that these fancy models are all worse than this very silly median. So that's kind of problematic. This is not that these models are bad. It's that this problem is very challenging, and we made a very challenging split of the data, and that's what you get. And we also tried some kind of good old random forest and good old multi-layer perception, and those improved over the fancy method. So from a machine learning perspective, this is an exciting problem to work on, right? Because there's a lot of things to do on how to learn from these limited data sets. So that's going to be that's actually the work we are doing at the moment. So to summarize, I discussed at the beginning that active learning enhanced with predictive models and generative models is a promising avenue for material discovery. I talked a little bit about this crystal GFRM method, which allows us to generate flexibly crystal structures, and how the lack of experimental data in this problem of discovering new solid electrolytes with high ionic conductivity makes it hard at the moment to use machine learning, and that's why we introduced Obelix, this curated data set of crystal structures and experimentally measured ionic conductivities at room temperature for lithium solid state electrolytes. And with that, I'll show this slide with a call for postdocs at the Institut Courtois, which is one of my affiliations, an institute in Montreal. Very nice and competitive conditions for postdocs, for those who might be interested. And yeah, and that ends my presentation. Thank you very much.
Thank you, Professor Hernandez, for your presentation. Now the floor is open for questions. If anyone would like to ask a question, please raise your hand.
We are fighting for questions. I go first. So Alex, thank you so much. Very nice talk. So I have several questions. Let's start with the data, okay? So you said you collected the data from previous data sets, and that probably come from experimental research, right?
Yes,
as you said.
yes.
Experiments, when even in the same institute, in 2 different labs, when they do, or even the same lab, we repeat it, we get different results for ionic conductivity.
Yeah.
And combining all this data set with maybe if they are same materials, how would you standardize that problem? Having, using different equipment, different environment, as we were talking in the morning, Alex Takov, he was saying about humidity problem, right? In different countries, and data changes, ionic conductivity changes based on that. So I'm just wondering, how did you take that into consideration, specifically like human error or the lab error, when you were standardizing this data?
Yeah, very good question. There's so much you can do, and we did a lot of different things. One thing was measuring these differences, actually. Unfortunately, I was checking if I had included this slide in the paper, and also I had a slide. I don't know how to refresh this page, but I have a slide with the links to the the data set and the code. So yeah, it's all available, by the way. But yeah, in the paper, we have this figure that quantifies the differences, so there's not a lot of cases, but wherever we found that for example, the same composition had been measured by in different papers. So we tried to analyze what the differences were, and there are indeed differences, but the conclusion was that it's not so bad. Okay. It's not so terrible. So, probably there's more things we can do. We are restricting ourselves to, what people have measured, and we are taking the data sets, cleaning it, taking the different data sets, filtering, cleaning, ensure that the quality is as good as possible. We humbly believe that it has improved a lot, these problems that I mentioned about the literature, but we won't claim it's perfect, and we won't claim that there's no biases and there's no problems. That's gonna always be there. But what I can say besides that is that we have to live with these challenges and be aware of them. And one way to mitigate it is this active learning loop I was talking about. The approach with this is not to train our model, make some predictions, and go home. And no, the approach is to train a model, when I say model, I mean train a predictive model, use it to train a generative model, generate data, and go and do more measurements, at least DFT, and eventually with the good collaborators do also experimental measurements to get new data, improve the predictive model, improve the generative model, and repeat until we go to the lab and get what we want. So it has to be an iterative process. So we are not especially with this kind of problem, we're not at a point where we can, just train a model and get some data, and that's going to be the next new material.
Yeah,
that's
I agree.
Not how it works.
And I think starting with experimental data is already a good starting point. So that's great.
Oh yeah. What we did find is that when it comes to DFT, there's a huge variance. There's so many. Actually, a PhD student in our group, she's working on it's work in progress. So I cannot say so much at the moment, but she's working on quantifying the time it takes to characterize the ionic conductivity with DFT methods, with machine learning potentials, with all the available methods. So the time it takes and the variability you get, it's insane. It's really bad, unfortunately, for this kind of problem. So yeah, that's why we stick initially to experimental data. Right. It's a kind of a golden standard we can have here.
So if we have time, can I ask very quick question? On the last part, so you have your standards already set very high about splitting the data set, and you see that the model is not doing very well. So what is the next step?
Yeah, there's a lot of different things. It's kind of challenging because there's really a lot of ideas. One way is to live with it and do what I said before. Okay, it's bad, but let's run a generative model and get new data, and from there we're gonna get improvements. So that's something we're already trying. Then other things we're trying is to I mentioned other data sets in this table. There's a lot more data. It's just kind of not clean and messy, but that doesn't mean it's useless. So we are trying to figure out from the machine learning perspective, what are the techniques we can apply to learn from these messy data sets that lack features. So you have to be smart from the machine learning point of view about how you incorporate this data in an effective way, and learn from that. And we'll have to. That's why we included these rigorous data splits to be able to measure whether we make progress or not. To be honest, the first attempts is that you mix data and no improvement, zero. So it's not enough to just include the data blindly, and no, that's not enough. We have to improve from the machine learning side of things. And the other third avenue is, so this is our experimental measurements, includes DFT data. There's a lot more DFT data, again, not super reliable, but same thing. Now we have the way to evaluate whether it works or not. So we'll try to mix as much data as possible and try if things get better or not. And again, do active learning and do these iterative improvements. Sorry, we'll talk